Hi all, today we are going to discuss about electric field intensity. So in the last class we have seen that if you are taking a charge Q1 and let us assume there is one more charge Q2 which is brought in the vicinity of the charge Q1, then there will be a force acting on this Q2 depending on whether both the charges are positive or negative. Let us assume both the charges are positive. Then there will be a force of repulsion will be acting on Q2 and it will be in the line joining the point 1 and 2. This I can represent by the unit vector A12. In this direction the force will be acting on this. This is what we have studied. And we have seen there the force acting on the second charge due to the first charge, that force is given by Q1 Q2 divided by 4 pi epsilon naught into the distance between these two is R12 square, and this will be multiplied with the unit vector A12 because this force is a vector quantity. So similar way, if I am taking some charge here, let us assume I am taking some charge saying Q2 is moved to this point. Now the force will start acting in this direction. This will be the force on Q2. So similarly, if you are moving to some other point, again force will act. That force will be acting in a direction, the line that is joining. That means what is the direction of this? Let us take it as some point number 4. So I am taking it as 4. So this will be A14. In this direction the force will be acting. There is the force acting on this charge. So similar way we can tell that wherever the charge is kept, the force will be applied on that, or that force I will be repulsive force if the charges are of same type, and the force will be attractive if the charges are of opposite type. So let us take the ratio of force per unit charge. That means I am dividing this F2 divided by Q2. That means this indicates how much value of the force will act per unit charge, or if the test charge is equal to 1 coulomb. If I are taking the test charge is equal to 1 coulomb. So in that case this becomes Q1 divided by 4 pi epsilon naught. That R12 is nothing but the distance. So I am directly writing distance square, and it is in the direction of A12. So this is called as the electric field intensity, or this is simply sometimes called as electric field. So this is electric field intensity. So the units for this is volts per meter. Volts per meter, because the units for the force is newtons. So this we can take as newtons per unit charge, or otherwise this generally units in electrical engineering we represent by volts per meter, because we are going to construct the electric potential, that means voltage V using the E. So these things we are going to discuss in the coming classes. So we can conclude that the electric field intensity is nothing but it is a force experienced on a unit positive test charge. So I am just defining the electric field intensity is the force experienced by a unit positive test charge kept in the vicinity of another charge. If you are keeping in the vicinity of another charge, how much value of the force will be experienced on the unit positive test charge. The units are volts per meter. So this I can represent as E2. In a simplified way I can write as Q, because whatever charge we are calculating that charge effect on the second charge. So I am simply writing Q only because only one charge is there here. This will become 4 pi epsilon naught into the distance is R12. So this will become R12 square into the unit vector we have seen in the last class. That unit vector will be vector divided by its magnitude. So vector is pointing from 1 to 2. So this will be R12 divided by magnitude of R12. The units are volts per meter. Here you have to remember the value of the Q will be in charge in coulombs. Epsilon naught also 8.854 into 10 to the power of minus 12, or otherwise this epsilon naught I can simply write whenever it numerical comes, just write 1 by 36 pi into 10 to the power of 9, because calculation will. Then how to calculate the R12 and other things we have discussed in the last class. So let us try to plot how the electric field will vary as you are moving based on this equation. So based on this equation I can write, if this is my distance R12, or as you are going away, so this is distance from Q. So this is the magnitude of R12. When it is varying, how the electric field will vary. So electric field you can see it is inversely proportional to the distance. So it is inversely proportional to the distance square. That is what we got. because this is anyway the magnitude of the unit vector. I am neglecting that. This is the one. So we can tell that as the distance is varying, that magnitude will goes on varying. So this is my value of E. So E will go on decaying as you are increasing the value. Now let us take for example, there are multiple test charges. Let us assume there are different charges. So I want to know what is the effect of all these charges at a particular point. Let us take it as Q1, Q2, Q3. Let us take it as Q4 and Q5. All these charges are there. So the effect of this charge on this one will be, you have to draw a line which is joining these two. So this will be the effect of the first one. This is F1. Force acting on this, or similarly because of this the E1 will come. So from this E1, so similarly this will be the value of E2. It is acting on this. Similarly, if you are applying this, so that will come. So this will be E3, this will be E2. So similarly because of E4 also, so E4 will come like this. So similar is the case for the E5. So if you want to calculate the net electric field at this point, the net electric field I can calculate by taking the sum of all these charges. So this I can write as 1 by 4 pi epsilon naught sigma k is from 1 to, let us assume there are n charges. So n number of charges are there. So this will become qk divided by rkp. Qk divided by rkpk, and it should be in the unit vector direction akp, where this qk indicates the kth charge and this rkp indicates distance of kth charge from point P. Let us assume this point is equal to P. I want to find at a particular point P. AKP is the unit vector pointing in the direction that is known. So in this way you can calculate if the point charges are given. But practically we doesn't get the point charges. Practically whatever charges we get, those charges are in a different form, because point form is not possible. The concentrated charges are not possible. Generally the charges are distributed. So if the charges are distributed rather than concentrated, so in that case we have to calculate the value of the charge. So different type of charge are there which are distributed. In that case, how to analyze? The first one is the line charge density. So generally the charges are distributed, then they are represented by charge densities. So charge density is represented by rho suffix L. L stands for the line charge density, and sometimes it is also called as a lambda in some books. So please don't confuse, whatever the notation they give, you can take it. So this rho L will be equal to dq by dl. Let us take for example, there is a line. So if you want to calculate dq at some small element, this will be equal to rho L into dl. Let us assume this length is equal to dl. So this is equal to dl. So from this I can calculate dq is equal to rho L into dl. If you want to find at a particular point, you divide this entire line into small blocks. Calculate the electric field due to each element. So this is the dE due to the small block. Like that you do the integration for the entire block or entire length of the line to get your total electric field. I am going to derive for the line charge density how to calculate. So from this I can calculate my value of the Q total value. If you want to calculate, this will be equal to rho L into dl. So similar way, it can be a surface also. So if it is on a surface, then it is called as surface charge density. So in the surface charge density is given by rho s will be equal to dq by ds. So dq by ds, or if you want to calculate the total value of the charge, we have to take the surface integral of rho s into ds. Let us take for example, this is my surface having a surface charge density of rho s. I want to calculate the value of dq at some small block. So this will be rho s into ds. Let us assume this is equal to ds, differential surface. So if you want to find at some point P, so this will be my direction of differential electric field. So similar way you have to do the integration for the entire area to get your total electric field due to all these things. Or we can tell that to calculate the electric field, this will be equal to surface integral of rho s by 4 pi epsilon naught r square. This you have to take in the AR direction or the normal direction. So this you all multiply with ds. So this thing we are going to derive in the next class. I will derive for the case of surface charge density how to calculate. Similar way, the third one will be there, which is called as volume charge density. Sometimes the charge may be existing in a volume. So represented by volume charge density, which is given by rho v is equal to dq by dv. So from that, if you want to calculate dq will be equal to rho v into dv. So you have to multiply with differential volume. So if you want to calculate the Q total value, how to calculate? Q total will be volume integration of this dQ, or otherwise this will be volume integration of rho v into dV. So using this I can calculate it. So in the case of volume, the volume will be there. So details of these things I am going to see in the next class. So today's class, let us see how to calculate the electric field due to a line charge which is having a very long line charge. So I am just calculating the field due to line charge. So before going to this, I want to remind you that below this description, in the description I have provided the link for the entire material. Because I am writing on the glass screen, so handwriting will not come properly. So only try to understand the concept here. You can download the material from the link below. You just go to the description, there the Google Drive link is provided. You can download the complete material from there. I have written the handwritten material there. Please download from there. So I am directly deriving here, because it saves our time also as well as the energy, because writing on the glass screen is very difficult. So this is y-axis and this is x-axis. So here I am only making the derivation. So remaining theory you please download from there. So this is my line charge. So let us assume the line charge is here. So which is having that rho L coulombs per meter square. This line charge is there. So I want to find at some particular point. Let us assume this is my point where I have to find. Let us take this is my height h with respect to this line charge. So at this point, let us assume this line charge is making an angle of alpha 1. Similarly, the second side of the line charge or the second edge is making an angle of beta 1 with respect to this one, or otherwise we can tell that it is making an angle of alpha 2 with respect to the x-axis to y-axis, or in this direction. Getting it? So let us assume the total length of your conductor is equal to L. This is my total length of the conductor up to this bisector. That means wherever the perpendicular line is drawn from the point, let us assume this length I am taking as L1. This length I am taking as L1. So now what I am doing, I am dividing this small line charge into a small differential length. So let us assume I am taking some differential length here. So in this differential length, so from view, what is the effect of this on this point? So that I want to calculate. So this will be equal to d, because it is the line joining this one with this one. Just now I have discussed. So right. So this can be resolved into two components. One component will be in the x direction and another component will be in the y direction. So we can tell that this is in the y direction. So this is in the x direction. So we can calculate the two components, the sum of those two components. That means you can represent in the rectangular form. Then we can combine to calculate the total value of the electric field. Getting it? So let us try to represent this diagram in a simpler way so that it will be more clear to you. So I am taking this y-axis and x-axis. So let us represent with a different color. Let us assume this is represented like this. This is my line charge. So I want to find at this particular point. So let us assume this height is equal to h. Okay. So I am representing again. So this angles, I am taking this as alpha 1. This angle I am taking as alpha 2, and let us assume this angle is equal to beta 1. So total length of this conductor I am taking as L. So up to this point, let us assume this length is equal to L1. So at a distance of x from this side, let us assume I am considering the small infinitesimal block. So this block, I am taking this block length is equal to dx, or the distance with respect to this center will be, because up to here it is L1, so this will become L1 minus x. At a distance of L1 minus x from the bisector, or at a distance of x from the origin, I am taking the point, I am taking a differential length dx. So because of this differential length, the force will be acting on this. So let us assume I want to calculate this force. This is my dE. So dE is having two components. One is dEx in the x direction. Similarly in the y direction, this is dEy. Is it clear? So let us take this point as r. Let us take this as small r. So let us assume it is making an angle of theta. It is making an angle of theta. Now let us try to apply the basic trigonometric laws and see how can we simplify this in an easier way. So from this, I can write my value of dEx. dEx is nothing but dE cos theta. And similarly, dEy I can write as dE sin theta. So let us take this as equation number 1. So, and I can write the value for the equation dE. dE is nothing but rho L dx divided by 4 pi epsilon naught r square. Remember, I am only taking the magnitude. If you want to find the direction also, you have to find the direction from that particular point. So that unit vector direction, whatever it comes, that you have to take. Let us take this as equation number 2. Getting it? So now, using this equation number 1, I can write this equation for in the x direction. I can write dEx is equal to rho L cos theta dx divided by 4 pi epsilon naught r square, because that rho L becomes rho L cos theta here. So this I am taking as equation number 4. So referring to this figure, I can write that L1 minus x is equal to h cot theta, because cot theta is equal to L1 minus x divided by h. You can just refer there. Okay, getting it? So from this I can write my value of dx. Dx will be equal to, this will become minus because differentiating on both sides, minus dx will be equal to minus h cosecant square theta d theta. So this I can take as equation number 4. And second one we can also define from this. I can write the value of the r. So r I can write as h cosecant theta. So this also you agree? So now what I am doing, I am substituting this equation number 4 and 5 in equation number 3. Let us try to substitute in equation number 3. When you substitute in equation number 3, so this becomes rho L. So dEx, so I am just substituting the values here. So this is rho L cos theta, and that dx, so dx I can represent by h cosecant square theta d theta divided by 4 pi epsilon naught into r I can represent as h cosecant theta. So I am writing as h cosecant theta whole square. So this, when I simplify, this will become rho L cos theta divided by 4 pi epsilon naught into h d theta. So let us take this as equation number 6. Okay, now the x component came. So x component due to the total length, if you want to find the x component due to the total length will be equal to ex will be, we have to do the integration. So here it is d theta. So the theta is varying from alpha 1 to beta 1. You can see here it is varying from alpha 1 to beta 1. Getting it? So that I have to do the integration of dEx. So this I can write as constant components I am taking out, rho L by 4 pi epsilon naught into h. This is fixed. Integration becomes integration from alpha 1 to that beta 1 I can represent as pi minus alpha 2. So this will become cos theta d theta. So if you do the integration, so this becomes equal to rho L by 4 pi epsilon naught h into sin alpha 2 minus sin alpha 1. So let us take it as equation number 7. So this is the component of Ex. So similar way you can derive for the component of y. So this I can write as dy is equal to rho L dx divided by 4 pi epsilon naught r square into sin theta, because it will be sin theta at that point and the distance is equal to r, that radius will be there. So now we can substitute the component of y and just derive it. So I am directly writing the answer. You have to solve in the similar way, substituting from the equations. So Ey will be equal to rho L divided by 4 pi epsilon naught into h into cos alpha 1 plus cos alpha 2. This is the y component that you obtained. Getting it? So now let us take different cases. So case 1. So case 1, let us assume it is at a perpendicular bisector. That means if you are taking this length of your wire, you are taking in the center, that point P in the perpendicular bisector. So this is my height h, this is the point P. The meaning of perpendicular bisector means the angle is same in the both the directions. That means both are alpha. So in that case, so what will be there? So let us assume the length is equal to L and this is rho L coulombs per meter. In this case, if you are taking the perpendicular bisector, so E will be equal to Ey only, because x component if you are substituting, Ex will be sin alpha minus sin alpha. Ex component will become 0, only Ey component will remain. So this will be equal to rho L divided by 2 pi epsilon naught h into cos alpha, because cos alpha plus cos alpha is 2 times of cos alpha. It will be in the normal direction. Normal direction means this is the direction, perpendicular direction to this conductor. That's why I have represented with AN. So this will be the equation. Now let us take the case 2. Case 2, let us take if the conductor is having infinite length. If the conductor is having infinite length, then this alpha 1 is equal to alpha 2, both will become equal to 0, because as it is approaching towards infinite, this will go on tilting, because the length is increasing, then alpha will go on decreasing. So this alpha will become 0. So in that case, if you substitute the electric field intensity, this will become, here we are taking rho L, right? Rho L by 2 pi epsilon naught H in the direction of AN. So this is the electric field due to infinite long conductor, as alpha is equal to 0. So in the transmission line, sometimes instead of rho L, they may represent with lambda. If they represent in the lambda, you can just substitute in the lambda. So this electric field calculations we are going to use in transmission lines. So there I will discuss in detail once we come there. So I request you that I have made one example also in this material. So please go through the material, try to solve the numerical. If you are getting it is fine. If you are not getting, please let me know where you are having the query. I will solve it. Because of time constraint, I am stopping here. I hope you have understood the basic concept of electric field intensity and how to calculate the electric field intensity due to a line charge. So next class we are going to discuss what is the electric field intensity due to a surface charge. So if you still have any queries, you can leave your comments in the comment section below. I will answer to your queries from there. Thank you. Thank you very much.